Thank you, Federico. Thank you very much, and thank you for pointing out the early time here. So you know any sort of mistakes that I'm gonna make, you can attribute them, all of them, to lack of coffee in the morning. So I'd like to thank first of all MPI for organizing this very nice virtual conference and for selecting our work. And my one little piece of advertisement is that a few months ago with Guillaume Chapuis, we would put up this paper on the archive, and this is a pretty large project. So I'm only going to be talking about one of the aspects of this project. So essentially we introduced this W-Laplacian matrix and has quite a few applications. So I hope that I'm going to advertise it enough for you that you can maybe go and check some of the other combinatorial applications of the W-Laplacian matrix as well. Okay, so my talk is going to be about yet another way to calculate volumes of root zonotopes, and this is joined with Guillaume Chapuis. Um, um, okay, so this is a problem. First of all, let me make clear that has been solved before in various cases, but always the solutions have various advantages and disadvantages. So that's why I'm feeling that like our contribution is interesting as well, and I hope you like it. So let me tell you a little bit about the story. All right, so the root zonotope, the zonotope for a collection of vectors, or in this case, for a collection of roots that come from a veil group, right? The zonotope is defined as the Minkowski sum of those vectors, and in my case, the root zonotope is going to be defined as the Minkowski sum of the positive roots of a root system. Okay, and so what I've drawn right here is the root zonotope for A2 for the symmetric group S3, and we see my natural selection of positive roots, no, 1 2 1 3 2 3, and this is the tiling of the zonotope. All right, so in this case I get a hexagon, it has 3 parallelograms, and it's very easy to see that you can label those parallelograms by, obviously the selection of roots that you chose, but that selection of roots that span the parallelograms, it corresponds to trees. So this one is spanned by the roots e1 minus e2 and e1 minus e3. So it's natural to represent it by the tree where one is connected with two and with three. All right, and this makes sense in the arbitrary case as well. And it's kind of like a really cool proof that the normalized, if you want, volume of the root zonotope is equal to the number of labeled trees on n vertices. And almost many, any combinatorial student, graduate student, or whatever, they would recognize this number n to the n minus 2 as the number of labeled trees. It's an important and common occurrence. And so I guess one thing that was a little bit under the rug is that the different parallelograms or the different parallelotopes that tile the zonotope, they all have the same volume. And the reason that they have the same volume is that the root zonotope for the symmetric group is unimodular. All right, so that's an important part of the picture. So let's say now, you as a combinatoric student or whatnot, you realize that a lot of the theorems that are very nice for the symmetric group, they are particularly nice because they're shadows of theorems that hold for all reflection groups or for all veil groups. And so you try to check the same thing, right? It's very easy to define the root zonotope. You try to figure out, is there an analog of this very nice product formula? So if you write down a few of the first volumes, for bit 2, you're going to get 7. For bit 3, you're going to get 3 times 29. That's a bad prime factor. And for B4, in fact, the whole number for B4 is prime. So, it's pretty bad. It doesn't look nice at all. And then, okay, D3 is 2 to the 4, but if you write that down, then immediately you're going to remember that D3 is isomorphic to A3. So this 2 to the 4, that's an accident in some sense. So all of the numbers, they factor really badly. What's going on here? Is there a reason to expect the product formula? Is there a reason not to? So let's see. There are in fact two reasons to not expect a nice product formula. And the reasons are that kind of like the things that work nicely for the symmetric group fail, but that's expected. So the other zonotopes are not unimodular, which means each of the tiles have different volumes. And even worse, the tiles are not really represented by nice combinatorial objects as trees. They're analogs of those things, but you don't have something very nice. And so the reason that these two properties affect the volume calculation is a classical formula by Seifert and McMullen that tells you that because in zonotopes, you always have these tilings that come out of collections of linearly independent collections of bases of the zonotope. So because of that, you have a very easy formula for the volume. It tells you that the volume of the zonotope is the sum of all of the volumes of the little parallelotopes. Or if you phrase it in a different way, you're going to have the determinant of the root vectors, in my case, that span the parallelepiped. All right, so this is relatively classical, and I want to realize it in the figure that I drew on the right. So this is B2, and you have a natural selection of positive roots as well, right? We have the two short roots here and the two longer roots, and this is a tiling of the corresponding zonotope. So if you notice here, right, almost all of the parallelograms have volume 1, but not all of them. So the parallelogram that is formed by the two long roots, it has volume 2. So that's, you know, that's part of it being not unimodular. I'm not going to discuss the tree interpretation in this one. In fact, BN does have a nice tree interpretation, but we're going to leave it. Okay, so because, however, root zonotopes are not just arbitrary zonotopes that come from root systems, you have a lot of the geometry of the reflection group to kind of like try and make use of. So for instance, how can I separate this number 2 with the rest of the number ones, right? Is it some invariant, some property of the underlying reflection group? So let me say that, oops, let's do that. So this volume 2, it corresponds to the reflection subgroup A1 cross A1 inside B2. And I also want to point out that there is another little parallelotope whose roots do not generate the whole group, and this one. And I'm going to say that this corresponds to the reflection subgroup B1 cross B1, right? So we know that these are equivalent, but I want to separate having short roots or large roots. So what I'm claiming here is that if you look at the roots of, if you look at the reflections that correspond to to the sides of these parallelograms, you're going to get reflections that generate some reflection subgroup, okay? And that this is a good idea, a good way to maybe group them together. So if you want to understand the Seyfert-McMullen formula, just group all of the bases of your zonotope with respect to the reflection subgroup that is generated. And there's a good reason to do that. And a good reason is this theorem by Baumeister and Wegener. In some cases, this was known before, but this complete statement was not. So this says that, like, if you have a collection of reflections, then the group that they generate, right, is determined only by what sort of Z basis the roots and the co-roots form. Okay. So, for instance, in this example right here, if I take the two short roots, they do generate the whole root system, but their co-roots do not generate the co-root system. So that's why you're living in a subgroup. If you check it for B1 cross B1, you will see that yes, they do generate the root system for B1 cross B1 and the co-root system for B1 cross B1. Okay, so let me not give too many details on that, but there is a nice characterization, right? And this implies that by grouping them all together, right, you can express the volume as some quantity that's related with reflection subgroups. You can say that the volume of the root zonotope, right, is the collection of all those sets of reflections that generate a maximal reflection subgroup, and you multiply that by the volume of the root lattice. So the volume of the root lattice is the same as this determinant calculation, is the same as the normalized volume of the corresponding parallelogram. So nothing weird is happening here. I'm just saying that, like, you can have a formula where a factor will be the number of reflection generating sets, and that might be a difficult thing to calculate. So let's see that to calculate that, we're going to make use of this new object, which is the W-Laplacian. So what is the W-Laplacian? The W-Laplacian is an analog of the standard Laplacian matrix for graphs, but defined for reflection groups. Right? I'm going to give you two definitions. They're equivalent, as you have many definitions of the Laplacian. They're both important. So in the first one, I want to determine a linear transformation that's given the following way. For all of the reflections of my group, I take the identity matrix minus the matrix that corresponds to that reflection. So this rho v is the standard reflection representation. Okay, there is a different way to phrase that. A different way is by kind of like adding all of the projections of an element V on the roots. So if you want to express it as a linear transformation, you start with an element V. What is its image? Project on all of the roots and add the corresponding vectors, and you get a vector, and that's a transformation. Right? So in the little picture that I have below, I want to point out how similar this thing is, that you should be able to recognize the standard graph interpretation of the Laplacian. So this is the complete graph K4, and if you do the graph Laplacian, right, you're going to get the diagonals are going to be the balances of the corresponding vertices, and then everything else is going to keep track of the adjacencies. All right, but like if you write it a little bit different, you can see that this is the sum of those um, um, essentially 2 by 2 transposition matrices where you have the ones in the diagonal and the minus ones in the anti-diagonal. And that's exactly what you get when you have an identity matrix and you subtract a transposition matrix. So this should be believable that yes, this is a natural generalization. And if you ask me about the other versions of what the Laplacian matrix is, which is, you have the adjacency matrix and you multiply it with a transpose, all of those things make sense here. It's one of those standard um, generalizations that work, right? It works. Okay, so whatever. I have this W-Laplacian matrix. Maybe I convinced you that it's a good generalization. Why is it good for me? It's good for me because it has very good numerological properties. So I wrote up again the 2 definitions just to be able to refer to them. I'm going to give you 2 important properties of the Laplacian matrix. This is in fact one of the coolest things that I want to advertise here, cooler than the formula for the volume, or more interesting. So if you calculate the determinant of the Laplacian matrix, you can do it many ways, but you have 2 ways that give you interesting results. So if you use the first interpretation here, it's the sum of the identity minus the reflection, then you're going to get that the determinant of the Laplacian matrix is equal to h to the n, where h is the Coxeter number of W. Okay, and this was, I guess, this sort of idea goes back to the definition of Coxeter numbers um, by Gordon and Griffith. So if you're familiar with this sort of representation theory of reflection groups, you would have seen this before. And it is one of those places that it is important. If you want to understand a little bit differently, what you see here is a central element. The reflections are closed under conjugation. So if you add all of them together in a bunch of identities, you have a central element, which means that this matrix acts by scalar multiplication. It's not very difficult to show that this scalar multiplication is by the Coxeter number h. This essentially is using that standard formula that says that the number of reflections is equal to hn over 2, something like that. All right, so in one calculation of the determinant, you get a Coxeter number to some power. I'm having a little bit of a comment here. If you have a reducible group, a very similar formula holds, but you have to take product of possible different Coxeter numbers because you have different irreducible components. Right, so here A2 will contribute the 2 3s, B3 will contribute the 3 6s, and F4 will contribute the 4 12s. It's like a standard thing. Now, if you look at the second definition that we had here, this is like as a matrix operator, right? This is a sum of rank 1 matrices. If you try to find its determinant, what you're going to think about, you're going to think how it acts on the trace of an exterior power of the space. And it's not very difficult to kind of use the trace interpretation and add all of the possibilities together when you have tensor product again and again. And what you're eventually going to get is something that involves, the sigma checks and the sigmas together in a Gramian determinant matrix. This is again a simple linear algebra calculation. I'm saying these things just to point out that it's not very difficult. And so these R's are C-linear bases, they just correspond to collections of roots that are linearly independent. And the determinant of Ri, Rj check, this is very similar to the Cartan determinant of the original group. But these aren't the simple reflections necessarily. This might be a different collection of reflections. So what you get is the Cartan determinant of the group they generate. So you get the connection index of the group they generate. And this is the second formula. The second formula tells you that the determinant of the Laplacian matrix is the sum over all reflection generating sets of maximal reflection subgroups times the connection index. And and the really cool thing here, I hope I'm not going to make it overcrowded. The really cool thing here is that somehow the W Laplacian sees both um, uh, the Coxeter number and the connection index. This is pretty cool. Usually they're different. Like in the symmetric group, they're the same, and they're the same for a canonical region, but in the other groups, they're different. But the W Laplacian kind of sees both of them, and in a way that we like, right? It's in its spectrum. Okay. So if you put these two together, you have a formula for the number of reflection generating sets. That's just by doing a Möbius transformation here and by using the Coxeter number interpretation upstairs. And I think this as a formula, it's interesting on its own. It gives you a relatively easy way to count the number of generating sets of a group. It's a little bit tricky here because you have to sum over, you have to have access to the poset of maximal rank reflection subgroups, but that's not too bad. And in the combinatorial types, it's very canonical. So anyway, a relatively easy to compute formula for the number of reflection generating sets. In the previous slide,
I have a
yes,
quick question. So
go ahead.
how hard will it be to see that inequality, that equality without, I mean, on its own? Would you say it's surprising?
Um, I mean, I would say it's surprising because of the Coxeter numbers appearing here. Like there isn't, is that what you mean, right? You're talking about this sort of equality. Yeah, it's a little bit surprising, at least to me, because of the Coxeter numbers appearing. Like there isn't a canonical way to think about it unless before you see the W Laplacian. After you see the W Laplacian, it's fairly straightforward. Yeah.
Okay.
I was not aware. I don't think there was something written down for reflection generating sets in yeah. Again, it's one of those quantities that maybe as a quantity it has been computed, but it's a bad number, so it's difficult to get nice formulas for bad numbers. Right? So anyway, so let me just, this is the slide that contains the theorem. And I, I do want to point out, this looks like a relatively ugly formula. Most of the formulas, I'm going to put a slide at the end, most of the formulas for volumes of root zonotopes have disadvantages. They might look good, but they might be very difficult to compute. They might look a little bit weird and be easier to compute. So ours has the slight disadvantage that it involves the Möbius function in the lattice of reflection subgroups, of maximal rank reflection subgroups. But on the other hand, it has what I consider an advantage, as like the Coxeter numbers, and it's easier to compute. It's much easier to compute. Okay, and the way that I get this formula again is the Seyfert-McMullen formula was standard. The volume of the root zonotope was given by a tiling. The volumes of the tiles were the volumes of the root lattices, and I just used the formula that I found before for the number of reflection generating sets. Okay. So again, this isn't something that we should look too closely here. It's just something that we can identify some of its characteristics. And I also want to say that like the same ideas work to calculate the Ehrhart polynomial. Instead of having an interval here that is between maximal rank reflection subgroups and all of W, you're going to have intervals that take reflection subgroups and their parabolic closures. And that would give you the coefficients of the Ehrhart polynomial. So, you know, things that you would expect to work out nicely. Okay, as an advertisement of the fact that this is an easy to compute formula, I'm going to cheat a little bit, but I'm going to do the calculation for E6. How do you produce maximal rank reflection subgroups? It's a very nice theory by Borel and de Siebenthal, and they tell you that if you start with your, Denki diagram for your root system, and then, you add the longest root and you get the extended one, then from the extended thinking diagram, just remove any single point that you want, and what you're going to get is a maximal rank reflection subgroup. To get all of them, you have to do the Dinky diagram of the dual as well, but this 6 is simply laced, so it's, you don't have to worry about that. And so if you remove here, we're particularly lucky because this is very symmetric, right? So you only have 3 options. Either you remove the one that you added, so you get the 6. You remove a middle one, so you get A1 plus A5, or you remove the center of symmetry and you get A2 to the third. So you really have two types of maximal rank reflection subgroups. And here is where I'm cheating. I didn't tell you how to calculate that you have 36 of those and 40 of type A2 to the third. But it's okay. It's another calculation that you can do. And again, if you want to use the computer, this is much easier, while the other formulas, even with a computer, are not. Anyway, so the lattice of maximal rank reflection subgroup for E6 is very simple. It has a bottom element and a bunch of atoms. So if you just apply this formula that we had before, step by step, everything that you're going to see is going to be three terms. The term that's coming from E6, so 12 is the Coxeter number of E6. The term that's coming from the reflection subgroups A1 cross A5, these are their Coxeter numbers. These are their connection indices in the Möbius function. So the connection index of A1 cross A5 is 2 times 6. The connection index of E6 is 3. A relatively simple calculation. You put them all together and you get a number like that. So it's almost a two-line calculation. Um, and if you're familiar with this problem, the other methods are quite more complicated. Okay, let's see. Yeah, so this was my little advertisement just for the calculation. I do want to say that like this term usually looks better. I'm not sure if I have a better formula for it on its own though. Let me say one more thing. So at the beginning of my talk, I described the tiling of the root zonotope for AN, and this was the same way that you get the volume of the permutahedron, and this involved indexing the tiles by trees. So do we have a version of W trees then? And so I want to give you two sort of ideas to compare. The first one is the matrix forest theorem. The matrix forest theorem tells you this is the case for the complete graph. So it tells you that you have the characteristic polynomial here of the graph Laplacian, and if you expand it, the coefficients of t to the k minus 1, they count rooted forests. A rooted forest is a collection of trees, and each of those trees is rooted. And I have here the case for n is equal to 4. Right? If you expand this polynomial, you get 4 to the third, which is the number of rooted trees on 4 vertices. All those are labeled. I just haven't put the labels here. Okay, and then here you have forests with 2 components. Here you have forests with 3 components, and here you have forests with 1 component. So there is an analogous, let's call it equation that holds for the W-Laplacian. And this is what I have right down here. So this is now the characteristic polynomial of the W-Laplacian matrix. Remember, it was a scalar matrix. All of its eigenvalues were equal to 8, the Coxeter number. And you can decompose it, and the coefficients of its polynomial, it's not immediate, but it comes down to summing over all parabolic subgroups. In the same way that here you have, two sort of different Young subgroups of S4. You have S3 cross S1 and S2 cross S2. And so in the matrix forest theorem, you were given that the coefficient had already an interpretation involving combinatorial objects. Here, the discussion that we had before for the W-Laplacian tells you that this sort of coefficient, what it counts is not exactly trees or an analog of trees, but it is generating sets weighted by the connection index of the group. So it is a natural analog of a tree, right? It's a generating set for the group, but it doesn't come on its own. It comes with a weighting. So that's kind of the idea, right? If you want to calculate the volume, you don't want the weighting or you want a different one, but the expression that has a nice formula has the connection index. So this is kind of like a good justification in my mind of like, why did the n to the n minus 2 formula not generalize, and what happened there? Okay, and so I have here a little bit of a slide that because it relates the existing approaches. Again, this is a problem that has been considered in the past. So Postnikov has given a very nice formula, but however, difficult to compute one because it involves a summation over all elements of the group. The continuum processes have given different formula that involves a summation over n factorial objects, and these are flags over the simple roots that generate the group. apart from the fact that these are expressed a little bit more uniformly, right? They're more satisfying in the eyes. They're also very good because they generalize to arbitrary permutahedra. So our formula does not generalize to arbitrary permutahedra because they're not zonotopes, right? Most of the times they're not zonotopes. And then a little bit closer to the way that we're thinking about things is this, you know, relatively recent project of Ardila, Beck, and Magwita, and many other co-authors. And all of these things involve giving generating functions for the Erhard polynomials, but they're efficient only in the combinatorial types. So somehow, when they think about the combinatorics of trees, they calculate the connection indices of groups, but like they don't use this terminology, right? And in our case, the result kind of unifies and touches the exceptional groups as well. So I guess I'm running a little bit out of time. The advantages of our approach would be maybe that it's more explicit. I guess this is arguable. The appearance of the W trees. And one last thing that I want to mention is that the definition of the W Laplacian, it involves kind of like a higher arithmetic role. When you have the arithmetic type polynomial, every basis is weighted by one of these determinants. When we calculate the determinant of the Laplacian, every basis is weighted by the square. So I've thought about it a little bit, but I'm not able yet to give kind of like a geometric explanation for that. So I'm just leaving it as an interesting thing. And with that, that's the end of my talk. So thank you very much.